Okay, I know that some of my juniors are going to be out testing next week, and we're kind of doing a difficult part of the HR diagram lab, 5.3.0. I'm going to apologize first of all. Number one, for the sound. For some reason or another, I can't seem to get the sound loud enough. Everything is on max, so I will work on that later. Have a limited time to do this, so all mistakes are just going to get left in. And understand that this is not edited, produced, or anything like that. So this is all my goofiness and all my mishaps all happening at once. Enjoy. What you'll need to do, we've already started these labs in class, so I'm not going to go over the first two questions. We already did that in class. So we're going to be looking at this section about Wein's law. And that kind of comes down here. Now, Wein's law has to deal with this little symbol right here. That is the wavelength, the maximum wavelength of light that we're measuring. What color of light that we're looking at. And remember, the color relates to the temperature. So this is Wein's displacement law as a way of measuring the color of the temperatures. So this is lambda. It's lambda max. That just means wavelength. This right here is, that's my funky, this is a lowercase Latin beta symbol. And let me make this picture larger so it's a little bit more visible on the screen. There we go. That's not a 6, that's a beta. So from now on, I'm just going to write that as a regular B, and we're going to just recognize that as being beta, okay? And that's a number that's given. That beta number is a constant. So this number is never going to change. So that constant is 2.898 to the negative third power meters times Kelvin. All right. And then the bottom part right there is the temperature. And that is going to be in kelvins. Remember, kelvins is the kind of more scientific way of looking at temperature rather than Fahrenheit or Celsius. It's actually measuring how much energy is in that object. All right, so that's the basics. That's Wein's displacement law. And that's all you really need to know as far as that is concerned. All right. So when we get to the question on the lab, question number 3, what it's going to do is it's going to tell you the name of the star. Let's save this for later. The name of the star is Antares. So I'm just going to do the first one for you. And that's going to be 9.3. Nope. That's not what it says. It says 934. See, I'm not getting rid of any of my errors. 934, and it says the wavelength nanometers at peak power density. So 934 nanometers is the peak power. That's the wavelength that it's giving off. That's going to give us a clue as to what the temperature actually is. Once we know this, we can figure out the temperature because I'm giving you the wavelength. So basically, just think about that. That's the wavelength max. That's this number right here. We're trying to solve for what is the temperature. Now, the first thing that you're going to notice when you're looking at the chart, when you're looking at this chart right here, is it's going to ask you to convert to meters because you'll notice that his constant, he is giving you that number in meters. This is in nanometers. So, let me resize this screen. There we go. You can block the old man. We don't need to see him. Okay, so if 1 meter is equal to 1 billion, that's 9 zeros, nanometers. Or we can say 1 nanometer is equal to 1/1 billionth. 1 nanometer is basically equal to 1/1 billionth of a meter. That's what we're kind of dealing with. We've got to convert nanometers into meters. That's a lot of zeros, and I hate writing that much. So if you look at it like this, instead of writing 1 billion with all those zeros, we can write this in scientific notation. We can say 1 times 10 to the, now how many times am I going to move my decimal point to get it behind this first number here? 3, 6, 9 times. There's 9 zeros there, right? So that would be like saying 1 times 10 to the 9th. Or in this case, we would have to move the decimal point all the way the opposite direction. That's like dividing by 10 times each time. That would be kind of times 1 times 10 to the negative 9th power. All right. Now that I know that 1 nanometer equals 1 times 10 to the negative 9th meters, or 1 meter is 1 times 10 to the 9th nanometers, I can use one of these formulas to determine how many meters is in 934 nanometers. You can guess. It's going to be a really small number, so it's going to be a negative number. So I'm going to take this number, 934 nanometers, and I'm going to multiply it by my conversion ratio, one of these guys right here. Now notice that nanometers is in the numerator, top of the fraction. In order to get nanometers to cancel out and meters to be my answer, I am going to need to put nanometers, that part of the conversion ratio, in the denominator. That way they cancel out. And meters are in the numerator, so that that would work out, because now we're going to say 934 times this number divided by this number, and meters will be in the numerator. And everything works out. So what do we put here? What numbers do we put here? Let's take the bottom one. 1 nanometer is equal to 1 times 10 to the negative 9 meters. Or I could have said 1 meter is 1 times 10 to the 9th nanometers. Now, at this point, if you want to use your calculator, this is how you would use your calculator. I would say 934 nanometers. I'm going to multiply that, so times 1, and you don't hit times 10 to the, you hit the EXP button. 1 EXP, oh, and I'm not doing that in the right screen. Let me start that all over again. Errors included. All right, so I brought up my calculator, my school calculator, the one that's on the Windows, right? Make sure it's not on standard, make sure it's on scientific. And I'm going to type in the nanometers. 934 times, and then I want to do 1 times 10 to the negative 9. That was this number right here. All right? So, 934, making all kinds of errors. Times 1, I don't have to say times 10. No, that doesn't work. 10, the power of 10 is an exponent. So you would say 1 times exponent, EXP, and it's a negative. So you see a little plus and minus. Don't hit the minus sign over here. The little plus and minus sign right next to the 0, you're going to click that. Notice it changes. It says E. That means times 10 to the, or exponent, negative, and that was 9. So you can see it says now 934 times 1 times 10 to the negative 9th power. And I hit equal, and that comes to an answer of 0.0000060 934. Now, if you put that down on your paper as an answer, cool. I'm good with that. But if you want to write this, let's keep this simplified so you don't have to write all these zeros. Look and see. Well, how many times do I got to move this decimal point to get it between the 9 and the 3, 4? 1, 2, 3, 4, 5, 6, 7 times. So this would be 9.34. I'm going off the screen here. Let me enlarge this up for you. 9.34. And I had to move it. It's a small number, so it's going to be times 10 to the negative. I moved it 7 times, 7th power. So in the next column, you would write 9.34 times 10 to the negative 7. And you would do it like this. 9.3, oops, not on the screen. So I'm writing in this column right here, 9.34 x 10, and I would type negative 7, and then I would highlight that negative 7, and if you hit Control period at the same time, that will superscript that number. All right, now we've got the actual wavelength that we can use in the formula. We have everything that we need to do this problem. We have the wavelength, which is this number right here for that star, for Antares. All right. We have the beta, which is the constant. This number never ever changes. And we're looking for the temperature. The problem is this formula solves for the wavelength. I need to find the temperature. Well, this takes some math that hopefully you guys got at a slightly earlier time than now. Hopefully you've been awake in your math class. How do you isolate a variable? Well, if we have the wavelength, my pen's going to run out on me, equals the beta over the temperature. How do I get the temperature to say temperature equals something? Well, the first thing I want to do is I need to get that temperature out of the denominator and into the numerator. So what I'm going to do is I'm going to multiply temperature over 1 by this. That comes out to be beta times temperature divided by 1. Well, if temperature is in the numerator and the denominator, they cancel each other out, and that's going to leave just beta. All right? But if we do that on this side, we have to do the same thing on this side. So we're going to put the temperature over 1. Uh-oh. That leads to a problem, because now it's going to be temperature times wavelength over 1, which is temperature times wavelength, because anything over 1 is what it is. So temperature of times wavelength, or that just means time. If I just write the two together, that's assumed that it multiplies. So temperature times wavelength equals beta. I still don't have the temperature isolated. I got to get rid of this wavelength. So I'm going to do the same thing. I'm going to take the opposite. So this is in the numerator. I'm going to put the wavelength in the denominator. They will cancel each other out, leaving me temperature. Excellent. That's what I want. But I got to do it on both sides. So beta times 1 over the wavelength, that will give us beta divided by the wavelength. All right. Now, that was me explaining how to do all this. But the reality is, for this entire question, you can use this formula over and over again, as long as you convert that wavelength from nanometers to meters first. Okay? So, now that we have the right formula, we're looking for the temperature in Kelvin. All right, so the temperature needs to be in Kelvin. If you remember, beta was 2.898 meters times Kelvin. 2.898 times 10 to the negative 3. And once again, if you've got lost and you're like, Mr. Lee, where did you get that number? That number is always 2.898 times 10 to the negative 3 power. Okay? So, and I just realized I made a mistake here. This shouldn't have said 2.898. It should have said 2.898 times 10 to the negative 3 power. All right, that just means that negative 3 just means it's a small number. If I were to write that as a real number, it would have come out 0.002898. I just moved that decimal point over 3 spots. So that number and this number are the same. So we're going to keep that. And that's going to be meters times Kelvin. And then we get the wavelength. The wavelength for Antares, if you remember, was this number right here. 9.34 times 10 to the negative 7. 9.34 times 10 to the negative 7. And that was in meters. Okay? So when I go to solve for this, meters will cancel out, leaving just some answer in Kelvin. Well, gosh, this is just math now. I just got to enter in my calculator this number divided by this number. But what might be throwing you off is, hey, everybody can use a calculator. That's cool. That's fine. But do you know how to use a calculator? That's the trick. How do you do that times 10 to the negative 3 divided by times 10 to the negative 7? Well, I'll show you. If I can figure out how to use this. Okay, so I'm going to make that small. And I'm going to bring up my calculator again. And I'm going to make mistake after mistake. Honest, guys, you're getting this. I'm not going to fix any of this. All right, I'm going to clear this. And I'm going to type in the top number, 2.898. That's Wein's constant. Times 10 to the negative 3, 2.898. So 2.898 times 10 to the negative 3. That's an exponent, so I'm going to hit exponent. That means times 10. And I'm going to hit the plus or minus sign. And I'm going to hit 3. That reads 2.898 times 10 to the negative 3. Then I'm going to divide that. So that was the numerator. We're going to divide it by the denominator, which is 9.34 times 10 to the negative 7. That's an exponent. So exponent 7 negative. So that reads 9.34 times 10 to the negative 7. All right. So I've got the first number. That first number is right here. It just converted it from the exponent to a real number. And we're going to divide it by this number. And I'm going to hit equal. And, okay, I get something with a lot of numbers here. Don't worry about it. Just look at the first 4 numbers, all the numbers before the decimal point, and the one right after it, so we know how to round. This is 3,100, and it says 2, but that 7's going to round that 2 up to a 3. So that answer is going to come to 3,102. And that's Kelvin. And that is the temperature of the sun, of that star, I should say, in Kelvin. And that's how those questions are done. You do that just for the next few stars, that should work. And this seems like a good place to end because now I'm competing with the announcements, so you guys know exactly what time of day it is. It's time for me to go home. All right, hope this is helpful. See you later.